Today I'd like to talk to you about the intensity of sound. We just finished the intensity of light and we saw how we could use it to figure out how much light is reaching different planets in the solar system and how much energy we can collect with solar panels. With the intensity of sound waves, some things are going to be familiar and work just like light, but there's going to be new things that are going to be quite challenging mathematically, so we want to take it kind of slow. I want to start out by having you guys realize that in terms of the spreading out of the waves, it's just like light. So you have your source of sound, or light. The wave comes off and travels out in a spherical shell. As it gets further and further out, the energy spreads into a bigger and bigger sphere, and the intensity of that wave becomes less and less. The light would become less bright, and the sound would be harder to hear. The equation that we had for light will still work when we talk about the intensity of sound. The power of the source of sound divided by 4 pi radius squared, where radius again is how far you are from the actual source of the sound. Realize that the 4 pi r squared is the surface area of the sphere that the energy has dispersed into. The units for intensity are going to be watts per meter squared. Unfortunately, that's not the end of the story because we don't usually measure sound based on intensity in watts per meter squared. Instead, we utilize a unit that hopefully you've heard of before called decibels. Okay? Mathematically, calculating decibels and working with decibels is a lot more challenging than most of the other mathematics that we've had to deal with. So let's see how it works. First of all, a little history lesson. Decibels is actually based on a unit called bells. And that was developed by the Bell Telephone Company almost 100 years ago. It was a way that they could measure strength of signals in a more easy to communicate way rather than using watts per meter squared. Bells became a little bit inconvenient and it seemed to make more sense to turn these into decibels. Realize the D just stands for deci, which is a metric prefix. So the base unit is the bell. And 1 bell is equal to 10 decibels. Deci refers to 1/10 of a bell. So it's a lot like centi or milli. It's just one that you don't normally encounter in most places in life. I'd like you to pause the video and I'd like you to copy down this chart showing the different decibel levels that we would experience in different circumstances. So you'll notice that I had 50 decibels in my classroom when I took that screenshot. There was nobody else in the room and there was no squeaky brakes from a bus right outside my window. Okay, and when I had 50 decibels, that correlates well to a quiet office where you still have things running like fans and computers and possibly printers. Okay, but you don't have a lot of conversation. Okay, that's about 50 decibels. Again, take a minute, get these down so you know what different decibel levels correspond to in terms of everyday sounds. We'd now like to take a little diversion. This is going to take us a couple days. This is not easy to learn about the mathematics that we need to work with decibels. Bells and decibels are based off of logarithms. So I want to make sure you know a little bit about logs, and I know you probably learned some in your algebra and your trig classes, but I want it fresh in your head, and I want to make sure you have the most important aspects for working in decibels. All right? So the first thing you should know about logs is there are 2 types. You'll find both of them on most scientific calculators. There is the log log, that's common logs. You'll also see an LA, that is for natural logs. Natural logs are incredibly important in lots of different areas, but for decibels, it's based off of common logs. It's based off of log base 10. So when you were learning logs, you probably learned lots of different bases. We're going to use log base 10, common logs, the one that is programmed into almost every single scientific calculator and goes by the key LOG. So what I'd like you to do is take out your scientific calculator and simply type in a couple numbers. Don't do all of these on the calculator. Just do enough to get the idea of a trend that you could then use to figure out the others much quicker than using a calculator. So type in the log of 10,000. Hit enter. Write your answer in here. Type in log of 10. Hit enter. Write your answer in that box. At this point, look at your answers. Look at what we were taking the log of and see if you notice what the trend is. Try to guess what you're going to get for some of these others. Like maybe start with this log of 100. What do you think you're going to get when you hit log of 100? Now try it on your calculator and see if it matches up with your guess. Then you can try guessing the answers for this one and this one. This one you have to think about what 10 million looks like. And this one I'd like you to try again on your calculator because that one might be a little bit surprising. But once you have this whole chart filled out, try to come up with a statement that explains exactly what is happening when you do the log of a number 1 followed by a given number of zeros. Here's how your answer should have looked. Pause it now if you have not written your conclusion. I don't want to influence what you say on your paper. Okay, when you unpause, hopefully you noticed that log of 1 followed by a number of zeros will spit out an integer that tells you how many zeros are present in your expression. So we had 5 zeros, 9 zeros, 1 zero, no zeros, and then -2 because it was a number that was less than 1 where we would have to move our decimal point 2 places in the other direction. All right? So hopefully you understand that the log of a number like this is going to spit out the number of zeros. Okay, if you were trying to work backwards, you say to yourself, what number would have a log that equaled 3? I hope you can do that at this point. I hope you realize that it's going to be 1 followed by 3 zeros. So try on your calculator doing the log of 1,000 and see if you do get 3. You should. You better. When you have a number like this, log of what number equals 10, it's going to be a 1 followed by 10 zeros. Now obviously you don't have to write out all 10 zeros. You could just write out 1E10, or you can write it out scientifically. -6, hopefully you realize you're going to have 6 decimal places, that is 5 zeros, and then the 1 for -6. So try it. Type in log of 0.000001, and it should tell you that the answer is 6. Working backwards for this one, you don't want to try and write out all those zeros. You definitely want to write it out using your E notation or your scientific notation, and that would be 1E81. All right, so working backwards should be no harder than working forwards. This number is just telling you the number of zeros. Okay, it gets a little bit trickier when we don't have a 1 at the beginning of our number. So I'd like you to go back to your calculator and try doing the log of 2 and see what you get. And then try the log of 20 and see what you get. And then try, without your calculator, just look at the pattern and see if you can figure out what the log of 200 is. If you can't, do it on the calculator. But at that point, I hope you can figure out what the log of 2 million would be without actually using the calculator. Do the same thing. On the calculator, do log of 5. Then see if you could figure out the other 3 without the calculator. And then if you'd like, check them on the calculator. These are how your number should look. And I hope you realize what is happening here. Your answer when you do the log of a number is going to be composed of 2 parts. The number in front of the decimal places tells you how many zeros you have. So I have none. I have 1. I have 2. I have 6. The number after the decimal tracks back to the fact that I have a 2 as my starting number. This will always be the same decimal if I am always starting with the same number in the front. All right? So with 5, it's 0.699, and again, that will stay the same for the entire time, and the number in front corresponds to my number of zeros. So you could again put a conclusion on how this works. The number in front of the decimal tells you how many zeros, and the number after the decimal is determined by the number in front. All right? So it's a little backwards, but this is how it works out with logs. Okay, so try to figure out what the x value would be for this one, and try to figure out the x value for this one. So what number would you have to take the log of to get this answer? What number would you have to take the log of to get this answer? And again, I gave you some help by telling you the log of 2 and the log of 5. So hopefully you saw that they're the same decimal part, and this has a 4. So I start with a 2 based on the 0.301, and then I add 4 zeros. So that would be 20,000. Here I know I start with a 5, again based on the decimal portion, and then I have 7 zeros. That would be 50 million. All right, so again, I hope you understand how you could do these without a calculator. If you know this, you should be able to figure out that. Okay, this might be a handy thing to have. The log of each whole number between 0 and 9, and then telling you again what the number in front indicates. So anytime your number in front is a 0, it means your answer is going to be in the ones place. If you have 1, it means you're going to have 1 0, so that's going to be in the tens place. The hundreds, the thousands, the tens of thousands, the millions, the billions, the trillions. So if you had a number like 12.301, I hope you realize you take the decimal part and say 2. You take the 12 and say trillion. That would be 2 trillion. If you go on your calculator and say log of 2 trillion, you should get 12.301. So having these 2 charts will help out a lot. Okay, so I'd like you to try going both forward and backwards. So pause the video and see if you can figure out what your answer will be without a calculator. Do not use a calculator for these. And then see if you can work backwards and figure out what x value would give you these logs. And if you're able to do this, you have a good understanding of how these logs are working. You don't quite know why we're going to use them yet, and we will get there, but at least you understand how to work with the logs mathematically. Hopefully you got these answers. Okay, tomorrow we're going to look at what are called log identities, which will take us another step closer to being able to use these things with decibels.